Nokia with this name? Yes, what's your name? Hello. All right, class. So in the last class, we had completed force between two parallel conductors. We had seen the two forces. Apart from those force per unit length, we had completed all the forces. Lorentz force got completed, magnetic Lorentz force, and all these phenomena got completed. So we have to start with torque on current carrying coil. Now, torque's whole phenomena, all these things will be utilized in a much better way in your next chapter, chapter number 5, that we'll be starting from the next class. It's Tuesday today now, so from Thursday we'll start with it. Right now, let's just see if a current carrying coil is placed, then what shall be the torque that will act on it and what will be the formula for it. So it's similar to whatever you have studied. And let's also see one more thing. Before, torque is what? Torque is the rotational force. So let's also see, we'll see two things. If a current carrying coil is placed in, this is placed in a magnetic field and the magnetic field is uniform, we'll see two changes. First change will be on the net force. Second change will be on the torque. What is the value of torque that is developed? Secondly, what is the value of the net force? We can get a formula, we can get any constant value, so that we'll see. So let's take a coil. Let's say I have taken a rectangular coil. More detailing of this and how torque gets related, that we'll do in the next section today. That is your moving coil galvanometer. This we'll do it in short. Most of the applications of it get utilized in the next lesson. That is your chapter 5, natural magnetism. So see, this is a rectangular coil that I have taken. Now let's mark some dimensions on this. Let's say the magnetic field, this is a uniform magnetic field. So the uniform magnetic field, this is B. B is the uniform magnetic field. Fine. Now the dimensions. If it's a rectangular coil, then definitely it will be having length, it will be having breadth. So let's say L I have taken as its length and B I have taken as its breadth. So L is the length of the coil and B is what? B is the breadth of the coil. All right, now one more thing. Let me take the angle. See, plane of the coil like this. Let's say this is the rectangular coil. Fine. So this is the direction of magnetic field that I have taken. Magnetic field is pointing where? Towards the right. By looking at the diagram, you can conclude the same thing. So if magnetic field is towards the right and the coil is placed like this, so I am taking this as theta. Do you understand? This as theta means the angle between the plane of the coil and the magnetic field. That is, I will consider it as theta. This angle, that is fine. So this is the angle that I have taken theta, which is the angle between the plane of the coil and magnetic field. Also, one more thing, let's take n, number of turns. It can be one for a single coil, and as the number of turns get multiplied or you start coiling it, the number of turns get increased. So number of turns. One last quantity. Let's say current, this is flowing in this direction. I have taken current I, and in all these segments, if I divide it as separate lines, let's say I is the current that is flowing. I is the current flowing. All right, in each segment. Now comes the derivation part. Firstly, we are calculating the net force. Net force means the translation force, not the torque force. All right. So for the net force, let's divide it into segments. Let's say this is A, this is B, this is C, this is G. Fine. I have divided into segments. Now, firstly, let's get the value of the magnitude of force. Net force will be obviously equal to whatever forces are of each segment. BA plus AD plus CD plus CB, all these four segments. Now, this formula, remember, we had seen a formula which related current, length, means length of the coil, magnetic field. That was F is equal to I L cross B. That formula we are going to use first. So see, generalizing way, I am just considering it, not taking separate sides. Let's say F is what? F is I L cross B. So definitely this will be I L B sine theta. Why sine theta? Because this is a cross product. Whenever you open cross product, you get sine theta. You do not take the cosine of it. Now the angle in this case, no, the magnetic field is what? The magnetic field is towards the right, and the coil has been kept like this. Can anyone tell me in which plane is the coil kept? Anyone from the class? Yes, Krishna?
YZ plane?
YZ plane, yes, sir. YZ plane it will be. Huzaifah, the question was in which plane was it kept? See, remember I told you some planes. If anything or your coil or any quantity or anything that is kept between the y-axis and x-axis, then you call it as the xy plane. If anything is kept like this, y-axis and z-axis, then we call it as the YZ plane in which this is kept, as rightly answered by him. Otherwise, the last plane possible is this, means x-axis and z-axis. Like so, these are the three planes. So this is also kept in xy. This is also kept in YZ plane. Now, one more question to all of you. Magnetic field is like this, and the plane of the coil is kept. Can anyone tell me what's the angle that is formed?
90 degrees.
90 degrees. Is 90 degrees. So for all the segments, it becomes 90 degree. Why? Because theta is the angle between plane of the coil and the magnetic field. So even if you're taking different segment, BC, AD, AB, CD, any other segment you're taking, angle won't change because angle is kept fixed between the plane of the coil and the magnetic field. So here sine theta, we'll take it as 90 degree, as you people have answered it. So this becomes ILB sine 90 degrees, that is ILB. Now let's calculate the net force. So net force will be due to each segment, FAB plus FBC plus FCD plus FDA, all these four segments. Magnitude for each segment will remain the same. For each segment, we will say the magnitude will be the same, but directions will change. Now, let's see regarding FAB. Let's just take it regarding FAB first. So for FAB, this was the rectangular coil. Current is flowing towards me. Current is flowing towards me. Can you see this in the coil? B to A it's going. That is, it is moving like this. So this is the direction of flow of current. It's flowing towards me. Now I have to curl my fingers where? Towards the direction of magnetic field. That's what we have studied. That place your fingers in the direction of current and curl your finger towards magnetic field. So even I could have kept it like this because this is the direction of current that is flowing. This is the direction of current. I could have kept like this, but I won't be able to curl it towards magnetic field. So what did I do? If I keep it like this, again current is flowing in this way, so I can keep it like this. And now if I curl it towards magnetic field, I'm curling it rightwards. So thumb is pointing where? Upwards. Means the force acting on FAB, this will be what? This is FAB and unit vector will be J cap. The unit vector here will be J cap. So let me write F only, or let me write ILB, it will be J cap. Fine. Now plus FBC. Let's move on to FBC. All right. FBCC. Current is flowing in which manner? This way. So I have to keep my hand like this. If I keep my hand like this, I'm not able to curl it towards magnetic field. If I keep it like this, because this is the direction of current, I can keep it like this, then I am not able to curl it towards magnetic field. If I keep it like this, then I'm able to curl it towards magnetic field. Thumb is pointing inwards into the page. That means minus K cap. So this becomes ILB minus K cap. Now, rest of you, all of you, right now, tell me what should be the force due to CD. So for BC, it will go here, FBC. All of you tell me what should be the direction, which unit vector should come for CD. All of you. And yes, you didn't answer. Who is this person with the name Nokia? Please enter with your real name. Yes, answers class. CD. So current is flowing from C to D. Okay, Krishna has answered. Others, only Krishna. Place your fingers in the direction of current. See, I'll tell you, current is flowing like this. Current is flowing like this. This is the direction of current that is flowing. So keep your fingers with the flow of current. Curl your fingers towards magnetic field. So it's up to you how you arrange your fingers so that you are able to curl it towards the magnetic field. So you have to place. Okay, so it was you, Avantika. Fine. It's your first class now today. Are you able to unmute yourself? Okay, okay.
Yeah,
All right,
sure.
Avantika. All right. So Avantika, this is the probably last class today that we have for this chapter, chapter number 4, magnetic effects of electric
Okay.
current. That is your moving charges and magnetism. From the next class onwards, that is the class that you have on Thursday, we'll be starting with a fresh chapter. So I hope you don't have any difficulties. And if you have any issues in any of the topics, so just let me know. You can text me in the chat box as well, or you can even text me on WhatsApp. So we can have a class as well. Or
Yeah,
I'll
sure.
send you the video lecture. Sarah, try again. Sarah, Atif is right. Sarah, just try again. So Avantika, I hope you have the ideas of all these magnetic field forces. Do you have idea?
Yeah, kind of. Yeah.
Kind of. I'll send you the video. We'll discuss this later. We can discuss that. See, others. This is the coil. Fine. Current is flowing like this. Yes, current is going into the page. This is the direction of current. So I have to keep my fingers either like this or like this. If I keep my fingers like this, I'm not able to curl it towards magnetic field, which is situated towards the right side. If I keep my hand like this, then I'm able to curl it towards the right side. So which unit vector is this? Downwards. That is minus of j cap. So I think only 2 students were able to do, Atif and Krishna. So this becomes what? ILB minus j cap. Plus last one class, try this, dA. Current, if this is your coil, current is flowing like this. Right, Krishna. Kulsum is also right. Correct, Atif. Others also try. If you are having difficulties, I'll explain you again. I'll explain you the law again, because these laws are very basic for the direction of force. Your answer will be incomplete without the direction of magnetic field, of magnetic force, all of these. If anyone is having issues, let me know. Hamza, your answer? See, listen carefully. This is the direction of flow of current right now. You get it? This is the flow of direction of current. So how can I keep my fingers? I can either keep it like this. So this is the direction of flow of current. I can either keep my fingers like this, or like this, or like this, or like this. These are the 4 possible directions for the flow of current. Now, if I keep my fingers like this, because this is the direction of flow current, if I keep it like this, then it's going upwards. So I have to keep it like this. This is the direction of flow of current. I have to curl my fingers towards magnetic field. Thumb is pointing outwards towards me. So the force here went downwards, FCD, and force is coming outwards, FAD. First, tell me, is the direction clear for all of you? Any
Yes,
doubts? If it's clear, then good. So FAD, it is pointing outward, and if it's pointing outward, the unit vector will be plus k cap. So can anyone tell me what is the net force? What's the value of net force that I'm getting?
0.
0. It's 0. So F net becomes 0. Force is what? This is your translatory force. Force required to move the object like this. This force is 0. So in exam, directly 2 things can come. Either to prove this force as 0, calculate the net force on a current carrying coil placed in uniform magnetic field. So you have to show this much. These 4 lines are enough. And obviously now you can easily for your examination at least learn that all the forces will point in all the 4 directions. So no need to waste your time everywhere just for confirmation if the figure is not given to you. If they give a figure by themselves and then they ask you to calculate the force, then obviously you have to check in which direction, because it can happen that they can give forces in different the values of current in different directions. But if nothing is mentioned, the question says calculate the net force on current carrying coil kept in uniform magnetic field. Simply show these 4 lines. Hardly it will take 2 to 3 minutes to solve the question, and it will save your time as well. So this is one thing. The other possibility of this question coming, how the question can come, is the possibility of getting on torque. Force is your linear force. Linear force means what? If there wasn't a linear force acting, no, some value of force was there, then the coil would be displacing like this way. There could be a forward displacement, or a backward propulsion in any manner. Right now, all the forces, upward forces, backward, lower forces, front forces, backward forces, all are balancing and cancelling each other. So that's why the net force is zero. It means, can anyone name the state when all the forces are zero? Equilibrium. Yes, Krishna. Your network issue is there, I think, Krishna, because every time you're unmuting yourself, your voice is cracking. But yes, good, right answer. It's equilibrium. Now, it's not a complete equilibrium. All right, it's a translatory equilibrium. It's in stable state. Right now, it's not moving. All the forces are balancing each other. But it can happen that this can rotate on its position, having all the forces zero. But in this way, it can rotate. And if it rotates, the rotational analog of force is what we all call it as torque. So two kinds of question can come. One, to prove this force as zero, or to calculate any other force. Rarely that comes. Mainly you have to show this net force zero, and it's very easy to do this. Even you can learn this. You know the final answer. So obviously you will get full marks in this. Second part that comes is torque. So torque is basically the formula of torque. Torque, you people know. All of you know what's the formula of torque. R cross F, that we have been doing. Now in electrostatics, we did a formula of torque in relation with dipole moment and electric field. What kind of dipole moment existed in electrostatics? Electric dipole moment, remember we denoted it through the symbol P, then cross product with electric field. So you don't just go into the details of torque. Torque we'll be doing again, because most probably in your chapter number 5, that is your natural magnetism. After covering those portion of magnets, bar magnets, natural magnets, we have these topics, and you get all the things that you studied in electrostatics. Those topics like equatorial field, equatorial point, axial point, everything will be repeated, and it becomes easier. If you people know, and if you have studied in your electrostatics, then it becomes easier to study here. So right now I was talking about torque. So torque, what we had studied, it was cross product of the dipole moment. What kind of dipole moment? Electric dipole moment. In the last class, we had seen magnetic dipole moment. Remember? We did. Can anyone tell the formula? Anyone from the class? At least look into your notes and tell. You must have written. All of you must have written.
Current into area.
Current into area. NIA. Right. If the number of turns are there, so NIA. Otherwise, if single turn is there, then as Atif said, it is IA. Fine. So this is M cross B. Instead of electric field, you will be having magnetic field. So the formula you can remember. It was P cross E for electrostatics. For magnetism, you have M cross P. Everything just in relation with magnetism. And you can open this and obviously write it as MB sine theta also. Otherwise, M, magnetic dipole moment, as rightly answered by Sarah, it can be NAI B sine theta. Now, this portion, sine theta, you can write, or even for simplicity, most of the times it is 90 degree, as seen for this coil, for a rectangular coil. This is the general formula. This is a general formula. Remember, NAIB sine theta. Sine theta will come. Why sine theta will come? Reason is that it's cross product. Obviously, sine theta will come. But right now, what's the value of theta? We know the value of theta. Theta is the angle between the plane and the coil, the magnetic field. So right now, we know it's 90 degrees. So this becomes NAIB. Why? Because sine 90 degree is 1. So coil will obviously not move. It won't slide backwards or forwards or upwards or downwards. This will rotate like this. This is the motion. It will simply rotate. So that's why we are getting certain value of torque. Otherwise, rotational equilibrium would have also been 0. So rotational equilibrium is not there. Some value is there. This torque will be used. Why are we doing in this lesson? Because you have to study moving coil galvanometer right now. After a few minutes, once you note this down, we'll be doing it. So that time it will get utilized. First, note down these things. Magnetic dipole moment. If you're not able to recall, look back into the notes. If you're still not able to understand, ask me. I'll help you with it. All of you were there in the class. This batch has a very good attendance. All of you are regular. So you people must have written, everyone. Okay, Aisha Rahman, this is your first class?
Yes, ma'am.
All right. Aisha, what's the current physics lesson going in your school? Right now, I mean, obviously, you must be having your vacations. Before your vacations had started.
Ma'am, for ma'am, we were on chapter 2.
Chapter 2. Chapter 2 had ended, potential and capacitance. And what about you, Avantika? Till the time others, the rest of you start noting it down. And what about you, Avantika?
Teacher just started magnetic effects of current. Just started.
This chapter number 4 just started. Before
Yeah.
the vacations are going in your school. Right.
Yes.
Fine. Written all of you? Yes, no, what? Done the writing portion?
Yes, teacher.
All right. Okay, sir. So others must have also done. This was short portion. Now let's move on to moving coil galvanometer. Now here you will get related to the torque portion that we have done just now. But before we move on to this actual topic which has been written in front of you, conversion of galvanometer into ammeter into voltmeter, both these things are in your syllabus. These come in your 12th exam, these come in your entrances everywhere. But before that, you have to understand what is actually this moving coil galvanometer. See, galvanometer is one device that you have in your syllabus, ammeter is another device, and voltmeter is another device. Voltmeter is very easy. By the name voltmeter itself, you will be able to figure it out that it's related to voltage. Regarding galvanometer and regarding ammeter, both of these can be confusing because both of them are related to current only. So how to distinguish galvanometer, this galvanometer that we are going to study? Most of you must have had your practicals, whoever had this, I think in your current electricity, you would have had this or in this lesson only. Galvanometer is such a device that is just used to detect current. Ammeter is a device that is used to measure current. For example, let's say 5 ampere of current is flowing through my circuit and a galvanometer has been attached to it. As soon as I'll be tapping on the key, means I've connected the circuit. The circuit is closed now. Current will be allowed to flow. As soon as the current will flow from the positive terminal, it will start flowing. The galvanometer will show slight deflection. Let's say now the current has increased. Instead of 5 ampere, it has reached to a level of 10 ampere. This deflection will increase. So I'll be able to figure, yes, current has increased, or initially current was low, or at least I'll be able to conclude the fact that current is flowing. Let's say I have connected my circuit, I have switched on the key, everything has been connected, but galvanometer is not showing any deflection. So it means that there is no current actually flowing in the circuit. There must be some error, some opening would be there in the wire, some cutting in the wire, or it can happen that I had not switched on the key. Sometimes we do not open the switch, no. So this can happen if the galvanometer doesn't show any deflection. So that deflection of the galvanometer, that is enough to show that there's a current. But as I've told you in the example that we took, whether the current was 5 amperes or the current was 10 amperes, using galvanometer, I am either getting this conclusion, yes or no, or I'm getting this conclusion that current is high or low. But what's the exact value of current that I'm getting? How will I know that 5 ampere of current is flowing? What if I don't know the resistance? I just know the voltage. So if I know the current's value, so I'll be able to get the voltage and other things. So that value, exact measurement, that is given by ammeter. Ammeters are devices that are separately given, that are separately available in the markets. Galvanometers are separately available. Voltmeter are separately available. But if you just have galvanometer and a resistor, what kind of resistor, that we'll see later on in this class only. But if you have these devices, then using just a galvanometer, you can do the work of ammeter, you can perform the work of voltmeter. That's what you have in your syllabus, known as conversion of galvanometer into ammeter and voltmeter. But now, before that, let's just see a mechanism of moving coil galvanometer. From this, it can come to tell you the principle of moving coil galvanometer. Principle at least can come in your short markers, like 1 markers it can come, or the construction part. Not in your long answer questions. In your, if it's a long answer question, your 5 markers, then some things will be included in the question. Like principle will be given, tell the principle, working construction of moving coil galvanometer, derive the expression how to convert galvanometer into ammeter, and by this it can give you a long question. Long questions also come in 2 manners. I hope you people have seen your previous year papers. One form is that it can directly give you section D, question number 13 is this, 1-line statement, 5 marks. Or it gives you in part. Question number whatever, 12 is this, A part for 3 marks, B part for 2 marks. So in this way also it can come, questions can come in your long answer question for your board exams. Now, moving coil galvanometer. So yes, it's a device used to detect current. But this device that is used to detect current in the circuits, that's just a galvanometer. I am constantly using the term moving coil galvanometer, moving coil. So we have just studied. What did we study? That the coil was there and the coil kept rotating. This was what we had seen. Why? Because of a force which we call as torque. It didn't move forward, backward. It just moved in the rotational manner because of torque. So similar thing, a device used to detect current. Basically, just understand the principle of it and you will be understand why we call it as moving coil, why this term is used. See, if a current carrying coil is placed in magnetic field, then this current carrying coil experiences a torque. All right. So if current carrying coil is placed in magnetic field and this magnetic field has to be constant, then it gets deflected due to the torque experienced by it. Just do one thing, note down this, we'll discuss it in 2 minutes. All right. So we were discussing, yes, the principle. So if a current carrying coil is placed in magnetic field that is constant, or you can directly use the statement uniform magnetic field, then it gets deflected due to, or you can say then it experiences current dependent torque. Then it experiences current dependent torque that tends to rotate it, that we have seen. It causes it to rotate. So that tends to rotate it and produce angular deflection. Angular deflection means angular deflection. Angular deflection. Deflection, you know, shifting, deflecting. Like this is deflection. This is known as deflection. Angular deflection means we are able to calculate this angle. We are able to measure this angle. That's why we are saying angular deflection, because this deflection, like if it is deflecting, no, like it's deflecting like this. If you look at from the top view, this angle, can you measure this arc? So that's why we call it as angular deflection. Now, apart from this, maximum thing that can come from here is the construction. Construction is rarely asked in your exam, but it can come. So construction, see how is it constructed. Have all of you seen galvanometers in your practical classes, in your schools, anywhere?
Yes, teacher.
Seen? Others, except for Atif?
Yes, ma'am.
Okay. So most of you have the idea of galvanometer. All right, Josefa. See, what you people must have seen. You must have seen, it would have looked like a device like this with the place for the connection of wire, black and red. Most probably it's given like this. And the markings are there and a pointer scale is there which gets deflected. That we are able to see. What's the mechanism behind it? Basically, there are permanent magnets. Some portion of permanent magnets are taken like this. This is the concave side of the magnet. This is, let's say, North Pole. This is South Pole. These are what? These are permanent magnets. All right, these are permanent magnets. Now, a soft iron core is kept between them. This is a soft iron core. Soft iron core is there. Now, at the center of the soft iron core, a spring has been embedded. A spring gets embedded. A spring gets embedded. Now, spring will be having two ends. A short spring, one end has got embedded in this soft iron core. What about the other end? The other end has a soft plastic material made up of plastic material. That is your pointer. So basically, it's like this. A pointer is there. Light-weighted pointer is there. And then you have the scale. So markings are there on the scale, but they are not of so importance because you don't get the exact value. But scales, this is the scale. So this scale is visible to us when you look at the galvanometer. No, these are the scales that you're able to see, and you're able to see what? You're able to see the pointer. Let me tell you, this is a pointer. All right. Now, the soft iron core is maximum time it is wrapped with copper wire or any conducting wire also. So it can be wrapped with it. But what's the main thing that occurs? Because of these concave sides, these concave sides of the magnetic magnets, the magnetic field lines are in radial direction, like this. Now this magnetic field is there, iron core is there. What will happen? All the things now relate. Whatever you have studied, now related once. Current carrying coil is kept in magnetic field. This is uniform radial magnetic field. Let me just mention this as well. This is uniform radial magnetic field. Fine, because of the K-vanes. So as the current carrying coil is kept in uniform magnetic field, it experiences torque which tends to rotate it. So as this gets rotated, the spring will get rotated and the spring will cause the pointer to move. So depending on the intensity, depending on the magnetic field and everything, the pointer will move. And that's how we are able to see the deflection in the galvanometer. Clear to all of you? Yes, no, any doubts? Answer. Or should I call the names and ask?
No doubts.
Others, Fatima, what about you? Fatima, clear to you? Hanifa, Hiba?
Yes, ma'am, clear.
Yeah? Kulsum, Sara, clear to all of you? Krishna? Fine. Now see, before you note down this torque that we were discussing, there will be two types of torque right now. One will be the restoring torque. Now we cannot go into the details of this restoring torque because obviously it will drag on our class. You must have done this in your waves and oscillation in your class 11th, last lessons that you must be doing. Restoring torque, restoring force, you must have done. I'll just let you know. Force was what? Minus of kx. Remember something like this you have done. Restoring force. In spring also you have done mass spring system, spring pendulum, this pendulum bob system, and different systems you had in your 11th class. If you convert it into rotational form, that becomes minus k theta. You don't have displacement in case of rotation. You have angular displacement. You don't have velocity. You have angular velocity. You don't have force. You have torque. Similarly, tau becomes minus k theta. So we won't be writing this minus sign because we are just writing the magnitude. Direction and everything, current we know. Next will be the deflecting torque. The torque that is causing the deflection, which you have studied in AIB. That torque that is causing the deflection. So both the torques are there and they'll be equal. So NAIB will be equal to K theta. Theta is what? Theta is the angular deflection. K is the torsion constant, a constant that you get to use. From here, you can take the value of theta, that is the angular deflection, that will be NAIB divided by K. Now, how to perform the conversions or how to do, we'll see one more thing, then we'll come into the conversions. Firstly, what is theta? Theta is basically angular deflection. K is torsion constant. K is the torsion constant. Before moving on to the shall we discuss sensitivity? These portions you have written. Okay, let's discuss sensitivity as well. See, sensitivity, it's a part of this only. Sensitivity means that how do we say, even in normal language, in common language, how do we categorize this word? So we sometimes say, this person is very sensitive. What does it mean when we are saying a person is very sensitive? If you will say something very little, that is not a big deal. The person can feel it. The person can feel bad because the person is sensitive. Similarly, now think in terms of galvanometer. Even if a small current is there, galvanometer is able to show deflection. It means then we call the galvanometer is sensitive. So similarly, the way we use it for human, it will be we'll call the galvanometer as sensitive, but the meaning of sensitivity will be different in case of humans and in case of galvanometer. So for a galvanometer, even if a slight current is there, galvanometer is able to recept it and is able to detect it. So sensitivity, when we use this term, sensitivity, it's not only about current, it's about voltage as well. A galvanometer is able to detect small values of current. Now we can classify it into two types, sensitivity, and this is a very small topic. And if it comes in your exam, the question will definitely, it will go easy way, because the questions are not tough from the sensitivity section. Till now whatever we'll do till sensitivity, direct questions come. Anything that can differ, it will be in the next part that we'll cover. So first is your current sensitivity, and second one is your voltage sensitivity. Current sensitivity means current per unit, basically the deflection per unit current. Current sensitivity is deflection per unit current. So what was the formula of deflection that we had got right now? NAIB divided by K. NAIB divided by K. Here also you have I gets cancelled. Current sensitivity is what? NAB divided by K. So basically current sensitivity is what? This is deflection per unit current. Easy, clear? You will be able to learn this. Deflect, because this is not a long derivation that it can come in your derivations. So you will be able to do it. Are you people revising the previous lessons? 4 lessons we have completed till now. Are you people even revising it? Because without revision, you'll forget everything. Many students who have got excellent scores in their board examination this time from Learnivio only. One student was, I think, Fazil Muhammad. He has scored 96 point something %. One has Abdullah has scored 94%. So these kinds of scores are there. For this, you require revision. Although all the 3 students kept on asking their doubts. You people also, if you face any difficulties and any doubts, just now we are on the group. That time I wasn't even added to them and with the group. They just had to organize a separate class, doubt class. So you people can send me your doubts or your queries on WhatsApp. If you're hesitating to send it on the WhatsApp group, you can send me personal. My number is there with you, all of you. If you have doubts, ask me. We'll be having tests of all the lessons, so keep on revising it. But right now we won't. After 5th chapter, we'll have the complete test. Deflection per unit current. Because it's you who has to study. Till the time you won't be revising. Ultimately, what will happen, even when a slight or very easy derivation will come in the exam, very, very easy derivation if it comes in your exam, then what, you know the final answer. You must be knowing the final answer. You'll be forgetting how to start it. From just, if anyone tells you the first line, no, you'll be able to catch up it. But that first line, nobody is going to tell you in the board exam. So it's better if you make a separate notebook for derivations. Soon we'll be having a test also only for derivations from the first 4 chapters. So at least you can just the derivation part that I'll tell you. I'll tell you on Thursday. So you will have a gap of 1 week, right? Today's test is there. But the next test I'll inform you. But as a suggestion, I'll tell you, because this only happens, even if you learn all the derivation, at the last it happens that you're able to not get the first line. It's like someone tells me the first step, like in drift velocity we did, for example, let's say. Then the first step is we have to write the value of time. Second step is write the value of current. Then write the value of charge. And the last step is take the value of current. From there we are able to get it. So similarly, things get mixed up. So it's better if you form a separate notebook or if you highlight all your derivations. All the derivations we have done it. All right. So voltage sensitivity is what? Voltage sensitivity is basically deflection per unit voltage. Now voltage, I can write it as IR using your Ohm's law. So this is current sensitivity and I can write this in this way. So theta was what? Theta was theta by IS. Theta divided by IS, you can see, not IS, basically theta by I only. IS will become current sensitivity, no? So let's just write I only. So theta by I is this term, NAB divided by K. And we have this resistance addition. That's the formula for voltage sensitivity. Even if you get the numerical values, the numericals value will be. The numericals from this portion we'll do in next class only. 1 or 2 numericals are there. Deflection per unit voltage. All right. Note down all these things. Now let's come into the main part that we were studying. This is also part that was also part of your syllabus. Now how to convert a galvanometer into ammeter. So conversion of galvanometer into ammeter. Let's say you have a galvanometer with you. Current I is coming. I is the current of the circuit, and the resistance of this galvanometer is G. G is the resistance of the galvanometer. Fine. In order to convert it into an ammeter, you have to connect a shunt in parallel with it. Shunt is what? Shunt is basically resistance. A resistor that is named as shunt. This is shunt resistance. Let's say from this IG has flown through the galvanometer. IG is the current flown through galvanometer. Hamza, can you tell me what will be the current flowing through this wire? Hamza, if from IG has gone, so how much current will be left in this wire? Kulsum? Yes, right. Josefa, right, correct. It will be I minus IG. So this will be I minus IG will flow. Hamza, clear?
Yes, ma'am.
Total current is I. IG has gone, so this much will be left. Shunt is just a name given. Why is this name unique, or why is this given? Because this is connected in parallel. Yes, so shunt is connected in parallel. And one more thing with the shunt is that it has small resistance. So as to measure high value of current, because here current is our prime concern. Now, if it is connected in parallel, Atif, can you tell me which quantity will remain same for both the shunt and galvanometer? Voltage, that is the potential difference. So potential difference across galvanometer is equal to potential difference across shunt. See, potential difference can be written as current multiplied by resistance. Here the current is IG, resistance of galvanometer is capital G. Sarah, what should be the value of potential difference for this? IG is the current, capital G is the resistance. Sarah. Yes, Sarah. Hiba. IG is the current flowing through the galvanometer, capital G is the resistance of it. I into G, yes, Sarah. It will be IG into G. IG is the current using your Ohm's law. V is equal to IR. Resistance is G, current is IG. So potential difference will be what? IG into capital G across the galvanometer. Across the shunt, it will be I minus Ig, that is the current flowing, and the value of shunt. So what's the value of shunt that you'll get? IgG divided by I minus Ig. This is how you will convert it into an ammeter. Now, second is conversion of galvanometer into voltmeter. Now, for voltmeter, suppose, let's say you again have a galvanometer and you have to convert this. So we connect a resistance in series with it. This is a high resistance. G will be the galvanometer's resistance. Capital R will be the high resistance. High series resistance, it is connected in series. So high series resistance. Ig is the current that is flowing through the galvanometer. So obviously current will be here the same. So Ig is what? Current flowing through galvanometer. Now across galvanometer, current Ig is flowing. Let's say potential difference of the system is capital V. So can anyone tell me? Not anyone, let me ask. Hiba, now can you answer? Capital G is the resistance of galvanometer. Capital R is the resistance of the resistor. What will be R equivalent? Total value of resistance, R equivalent. Hiba, can you try? I'll help you if you're wrong. Never mind, you'll be able to remember it for future. You'll be able to remember the derivation. Just tell. If two resistors are connected in series, what's the resultant equivalent that we get? Fatima? Are you people even revising? I think I have to increase the frequency of tests then. Yes, Krishna?
R plus G.
R plus G. Definitely it will be R plus G. Only few students are able to answer. This question we have done, equivalent resistance, we have calculated it for series, for parallel. Are you people not aware of it? If this is the rate that you people show in answering the questions that are so simple, then we have to increase the frequency of tests, or I'll be taking your Viva daily in the class. See, R equivalent will be what? This is your first resistor, this is your second resistor. So the R equivalent will be simply R plus G. Now use your Ohm's law. V is given, R equivalent is given, current is Ig. So V will be equal to Ig into G plus R. From here, this is why, because V is equal to IR. So from here, G plus R can be written as V divided by Ig, and the value of resistance can be written as V by Ig minus. That's how you calculate the value of resistance in case of voltmeter, and series high resistance is connected. In the ammeter case, shunt has been connected, which is of low resistance. Tell me, all of you, is it now clear to all of you? Hiba, did it get clear?
Yes, ma'am.
Fatima, what about you? Now are you able to understand? Huzefa, Kulsum, Sarah, others also. Fatima. Avantika, you able to relate it?
Yes, ma'am.
All right. Fine, class. So note down, this is All right, class. So I think you people must have written one question we'll do so that you get familiar with this numerical and how the numericals come in your exam. But that question we'll do in the next class only. Is Avantika right now? Avantika, we are going to have a test right now. So just look at the question paper, take the screenshot of question paper, keep it with you. Or if you think you know the answers, you can even attempt the test. That's up to you. But others, let's start your test. Questions are easy. 3 questions are there. All of you will be able to do. Whatever suits you, Avantika, it's up to you for today's test. You're exempted from today's test. If you think the questions are easier, you will be able to handle them, then attempt it. Otherwise, you can take the screenshot of the paper and solve it later on. Last 10 minutes are left now. So all those who are end of the paper, you can wrap up your paper now. 10 minutes left. Yes, Atif. Atif, I've received yours. You can leave the meeting.
Thank you, teacher.
Yes, Josefa, I've also received yours. Yes, fine, Josefa, you can leave. Kulsum, yours have also received. Yes, class, time is up. Hamza, Hiba, Krishna, Sara, hurry up.
Ma'am, I'm sending, but due to weak net, it's loading.
What happened, Krishna? What's it showing? Loading. Yes,
Yeah, ma'am.
received, Krishna. Received.
Thank you, ma'am.
Sara also. Sara